All right, so we've been talking about acid and bases here in this chapter, and at the end there, the first part of this lecture, we got into what we do with strong acids or strong bases. So as we talked about, if you're given a formula, pretty much I would say in this particular class, you could probably safely assume that it's a strong acid or strong base, because weak acids and weak bases, if you want to calculate the pH, is a much longer calculation, and you usually don't talk about that until Chem 1B. So probably a pretty good idea that if you see an actual form, it's probably going to be a strong acid or base. But again, knowing those 6 strong acids is definitely something that can help you with that. And like I said before, if it's not one of those 6 strong acids, then it's probably going to be weak. Really, the goal here, if you have a strong acid or strong base, is really for an acid, you want to make sure you get the H plus concentration. And for the base, you want to make sure that you get the OH minus concentration. That again will allow you to get the POH. And for the strong acid, that would allow you to get directly the pH. For the strong bases, as we talked about, you got to do an additional step. After you get the pH, you do have to kind of convert it into the PO, from the POH to the pH there to get it. So why don't you guys try these couple examples here and see what you come up with. We want to know what is the pH of a 0.025 molar perchloric acid solution and a 0.025 molar calcium hydroxide solution. Okay, so let's take a look. So first off, we have 0.025 molar perchloric acid. Once again, perchloric acid was on that list of strong acids, so what we know that this is definitely a strong acid. And in this particular case, what that means is it will, like all strong acids, pretty much 100% break apart into ions. And really, again, here for our pH, it is the H plus concentration that's important. So we have 0.025 molar of the whole thing. Again, we could just simply do kind of a mole to mole relationship. It's a 1-to-1 relationship, which means we would just take 1 times that concentration, which means it's not going to change. And that would give us our concentration here for our H plus. And that really is what we need to calculate the pH. So we can now go into our pH, negative log of 0.025. And that's going to give us a pH here of about 1.60. 1.60 is definitely acidic, which is what we would expect here, obviously, with an acid in this particular case. Once again, 2 significant figures, 2 decimal places there on the pH. Any questions on that one there? Now, if we look at the second one here, I definitely see hydroxide. So this is definitely a base, and it is going to be a strong base. Remember, again, if you kind of roll down group 1 to potassium, hang a right there to calcium and down. Again, any of those guys in kind of group 1 and group 2 with hydroxide most likely will be a strong base. And that means that this is a strong base. So it's going to do pretty much what a strong base will do and a strong acid will do. It also will break apart in solution. And in this case, we will get a calcium ion, and we will actually get 2 hydroxide ions. Again, because there's a 2 here. That means in this case, it is the hydroxide concentration is what we're interested in. And in this case, it is a 1-to-2 relationship here between these 2 guys. So to get the proper concentration for the hydroxide, we would need to multiply the concentration by 2 so that we actually get the proper hydroxide concentration. And that would be 2 times 0.025. It's going to give us a 0.05 molar. And that would give us, once again here, the hydroxide concentration, not the H plus concentration. So again, that's important because that is going to allow us to calculate first the POH, right? So the POH minus the log of 0.05. That's going to give us a POH here of, call it 1.30. Now, if for some reason you did this and you thought that this was the pH value, it really shouldn't make sense to you, right? Because this is a base and clearly a pH of 1.3 is acidic. So if you for some reason thought that this was the pH, logically thinking it shouldn't really make sense. So we do need to calculate the pH here, and that's probably easily done by doing our 14 minus our pOH, and that would give us 14 minus 1.30. And if we take that there, that gives us a 12.70. Now that is more like it, right? 12.7 is definitely basic, which would go with this guy here. That is a base. Any questions on that? Now, I will say that probably in the case of having to worry about this sort of adjustment here, probably it's going to be your bases where you're going to probably run into that more than your acids. Because if you look at that list of like 6 strong acids that we listed, pretty much 5 of the 6 or so are pretty much monoprotic, which means they have just one hydrogen, which means in most cases, if you have a formula of a strong acid, that probably is going to be your concentration of your H plus, like it was in that experiment we did last week when you took the HCl and then you diluted it, and then you took the HCl and diluted it again, and you wanted the hydrogen concentration. Again, because that's a strong acid, it's a one-to-one relationship, it's monoprotic. Whatever the concentration of the acid is the concentration of the H plus. But once again here, probably with the bases that come from group 2, probably the only time you might need to do some type of adjustment on that. Any questions on what to do with strong acids, strong bases, pH? Again, probably won't come across any weak bases or acids in terms of pH calculations until you get to 1B. All right. So the last thing we're going to talk about in this sort of chapter here is buffers. And we also saw a buffer in the experiment that we did last week. Buffers, again, are solutions that have the ability to resist changes in pH when you add additional acid or base to it. Again, as I mentioned last week, a buffer is not necessarily a neutral solution. So you can make a buffer at any pH you want from 0 to 14. You could choose it. You could figure out how to make it. And you actually could just make it pretty much whatever pH you like, and you can make a buffer solution. Again, sometimes people have a misconception about that. They think buffer has got to be a neutral solution. Again, that's not the case. Definitely could have an acidic buffer, could have a basic buffer, could have a neutral buffer. It doesn't matter. What makes up a buffer is a combination basically of one of two combinations. It's either a weak acid and the salt of its conjugate base, or you can make a buffer up of a weak base and the salt of its conjugate acid. A buffer cannot be made up of a strong acid or strong base. So you cannot have a buffer out of a strong acid or strong base. So that is a really important key component to a buffer is it has to be a weak acid or weak base. Now, the reason for that is a buffer is able to withstand changes in pH when you add acid or base. And what we're talking about here is really big swings in pH. So um, as you saw, for example, in your non-buffer solution of water, when you added a little bit of acid, the pH jumped pretty quickly, right? It didn't take that much to move the pH a lot of units. As you saw with the buffer that you made, 200 drops later, right, maybe the pH moved, right? It took a lot of acid to get that buffer to change pH. Now, the reason why a buffer is able to resist really big changes in pH, big swings in pH, is because it has both of those things in there. So, for example, if we talk about our weak acid and conjugate base, are the salt of a conjugate base. So for example, if I had acetic acid, that is a weak base. And if I mixed it with sodium acetate, that is going to be my conjugate base in this case. And that is pretty much the buffer that you made in that experiment, right? You took a shot of sodium acetate and you added some acetic acid to it and you made a buffer. What is that definition? This definition here is still our Bronsted-Lowry definition, which means the only difference between those two things is an H plus. Now you may say one's got a sodium and one doesn't. And that sodium there is really what makes this what is referred to as a salt. And a salt is an ionic compound. This sodium acetate is really a sodium ion and acetate ions. It is a strong electrolyte, which means when it's in solution, it will not stay together and it will break apart. And that's different than over here, for example, our weak acid, which is a weak electrolyte, which will mainly stay together. So if you remember when we talked about electrolytes, weak electrolytes will mainly stay together, but will break apart a little bit. So it will set up that reversible type reaction in this case. So what is the actual buffer part here of this solution if you put these together? It is the acetic acid and it is the acetate. And now if you just look at those two, the only difference between those two is 1H plus, and that is your Bronsted-Lowry definition. What is the sodium doing? It's really not doing much. It's floating around, having a good time. It is really a neutral salt, is what it's referred to. It's like a spectator ion. It's just floating around. It is in there, but it's not actively part of any type of buffer situation. Really, the reason why sodium ions are not part of the buffer situation is it actually comes from a strong base, like sodium hydroxide is where that sodium would most likely come from. And if you remember, the relationship between an acid and its conjugate base, or a base and its conjugate acid, is if it comes from something relatively strong, it will be a relatively weak conjugate partner. And if it comes from something weak, it will be a relatively strong conjugate partner. And that's the idea here. Sodium ions come from sodium hydroxide, which is strong, and that's relatively weak, which makes it kind of neutral. You don't have to worry about it. So the purpose of a buffer and how it's able to work correctly is when you take both of those things, they are going to be in the beaker together. So what's really going to happen, for example, when you add your acetic acid in, because that is a weak electrolyte, that guy is actually going to set up an equilibrium in the beaker. It will break apart a little bit, but mainly stay together. And it will stay together as acetic acid, and it will break apart a little bit into H plus and acetate. So when you put that acetic acid in there, because it's a weak electrolyte, it's going to set up both of those things. Now, when you put the sodium acetate in there, you are actually adding a little bit more of the acetate. You're kind of building up the acetate. Remember that the acetic acid is weak, so you are going to get a little of these guys, but not a ton. So you're going to kind of beef up the acetate part here by adding some more sodium acetate in there, and that's going to kind of beef up the acetate part. So when you start with your buffer, what you will have is a pretty good concentration of acetic acid in the solution. And because you kind of add a little bit more sodium acetate, you'll also have a pretty good concentration of acetate in the buffer. And that's really important because you could think of this as there is an acid part to the buffer, which in this case is the acetic acid. And there's also a base part to the buffer. And that is critical for how a buffer is able to actually function correctly. You need to have both of those things in there. That is also why you cannot have a buffer that's made up of just a strong acid or a strong base. So for example, let's just say you wanted to make a buffer from hydrochloric acid. And you're like, well, I have hydrochloric acid, which is HCl, and I have this conjugate base, which is Cl minus, right? So I have my acid and my conjugate base. Can I just make a buffer from some HCl and like sodium chloride and put them together? The problem with this is when you would go put the HCl into this solution, it's going to 100% break apart into H plus and Cl minus. You're going to have none of the HCl units still there. And then if you decided, well, I'll just throw some sodium chloride in there, all you're going to add is some more chloride and some sodium. And the problem with this is you do have a conjugate base in this solution, but you're missing the acid part because it's basically broke apart. So there's no acid in this buffer solution if you're trying to make, which is really not a buffer. And what that means is it will not be able to act as a buffer because you only really have one of the components there. You only have like the base part. You don't have the acid part of it. So having a weak acid or even a weak base could also do this. It will be able to set up that equilibrium and you'll be able to keep both parts of that guy in solution, the acid part of the buffer and the base part of the buffer, which is extremely important for how a buffer actually works. Any questions on that there? So what happens when we do add, say, acid or base to a buffer? What happens, for example, is let's talk about what happens actually when we add it to a non-buffer. So as you saw in the experiment, something like water is a non-buffer, water. So if we take water, a beaker of water here, and we just have water basically, and we decided to add some hydrochloric acid to this beaker, kind of like what you did there. What's going to happen in this case is, once again, that is a strong acid, which means that it is going to 100% break apart into its ions in water. And what that means for water is when you add this, you get 100% of these guys, which means you just put in there a bunch of H pluses. And they're going to be freely floating H pluses. And as we talked about, the pH is related to the amount of H plus that's present. So in this case, what you just did is you just added to that solution a ton of H plus. So the H plus concentration basically just jumps up really, really high. And the result of that is the OH minus concentration goes way down. And the pH in this case actually drops way down. So what you would see in this case, for example, if you took pure water, which say is a pH of 7, and you added your hydrochloric acid to it, it would drop maybe from like a pH of 7 down to like a pH of 2, a really big jump in pH with not a lot of effort. And again, that's really what you saw when you did the experiment last week. Probably for most of you, just a couple of drops of the HCl was enough to move the water pH color down 1 unit of pH, right? And that was just a couple of drops, right? And it changed one whole unit of pH by just adding a little bit of acid. And that's because it has no way to stop the influx of H plus onto that solution in this particular case. So all you get is just a bunch of H plus that basically piles up. Now, what happens if we took a strong base and we added it to water as well? So if we took another beaker here of water and we decided to add some sodium hydroxide to it, which is a strong base. When we add that sodium hydroxide, because it also is a strong base like our strong acid, once again, we're going to get 100% of it breaking apart into ions. There's going to be none of the whole unit still together. We will have 100% of those ions basically floating around in that water. And basically what will happen is we will now produce a bunch of sodium ions, which is not that important. But more importantly here, we will produce a ton of freely floating OH minus ions in solution. And it is that presence of OH minus that's going to go way up. And remember that because OH minus and H plus are tied together, the amount of H plus will go down. The result of that is your pH will go way up. So again here, if we started with water at like a pH of 7 and you added a little bit of sodium hydroxide to it, it would maybe go from like a pH of 7 up to like a pH of 10, 11, a really big jump in pH. And that again is really for the reason that the water has no way to stop the formation of those free OH minus ions that are coming into the solution and going to cause that pH to go pretty crazy. Any questions on what happens in a non-buffer? Yeah. Say again. Do you need to use a weak electrolyte for uh for a buffer you do need a weak electrolyte. But if you're asking you know, in terms of the hydrochloric acid and sodium hydroxide, is that what you're asking? Or yeah, so this is why you do need something weak. We're going to talk about it here in just a second, but yeah, you do need a weak because a weak acid or weak base will allow you to keep in the solution to start with both the acid part of the buffer and the base part of the buffer. If you try to use either one of these, pretty much that's what you're going to get on the right hand side. You're not going to have actually a buffer present. You're just going to actually change the pH a lot because you're adding more H plus and OH minus. So let's talk about what happens when we add these guys to a buffer situation. And we'll use a different buffer. We'll use something like HF, which is hydrofluoric acid, and say sodium fluoride. By the way, I know this is a weak acid because it's not one of my 6 strong acids. So that's a pretty good guess. This is its salt of its conjugate base. And those two things together will make a buffer. And once again here, this sodium fluoride is a source of sodium and fluoride. It is the fluoride part that's actually the buffer part here. So the real buffer components is the HF, which is the acid part of the buffer. And again, it's actually the F minus that is the base part of the buffer here. And once again, as I mentioned earlier, you can use the Bronsted-Lowry definition there. And that is, again, just one H plus difference between them. So if you're trying to decide, can this thing be a buffer? The first thing you want to determine is that a weak acid or weak base? And the answer, if the answer is yes, that's a weak acid or weak base, the second thing you want to make sure is his partner is conjugate partner is the only difference between those things, basically an H plus. So those are two things you want to kind of look at. So what's going to happen when we make this sort of buffer here is we will have our beaker, and when we put our HF in there, because it's a weak acid, it will set up that equilibrium in the solution. And it will break apart a little bit because it is a weak electrolyte. So it will be able to produce a little bit of ions in that solution. And we will have our buffer. We're going to help it by adding our sodium fluoride, which will give us a little bit more of fluoride in there. So now in this solution, we have a pretty good part of this buffer, which is the acid part of the buffer and the base part of the buffer. So if we were going to take the hydrochloric acid like we did with water, and we decided we want to add our hydrochloric acid into this buffer here, because it's a hydrochloric acid, which is an acid, it is going to react actually with the buffer. And it's going to actually react with the base part of the buffer in this case, which is the F minus. Now you can leave the sodium on there if you like, or you could take it off. It is your choice. But it's basically going to do a double displacement reaction here. And we're going to switch partners. And it's going to make sodium chloride and HF. So when we react this with our buffer, the hydrochloric acid is a source of H plus and Cl minus, basically. And what we create are actually two things. We create this guy, which is a salt. And this is what is known as a neutral salt. That is because the sodium, as we talked about, basically comes from sodium hydroxide. And the chloride comes from hydrochloric acid, which is also strong. So these guys are really neutral. They're not going to do much to the pH or mess up the pH because of that. So these are neutral. Basically, their pH is like 7, basically, not going to mess up the pH. We also made hydrofluoric acid, which was there to begin with, which means clearly that is not going to screw the pH up in this particular case. And that always happens in a buffer. When you add something like we did here, hydrochloric acid, to a buffer, you will actually use up some of the base part of the buffer, and you'll actually make some of the acid part of the buffer. And it's almost like regenerating itself. So you'll use a little bit of the base, but you'll make a little bit of the acid part of the buffer, and it'll sort of regenerate. It is actually what we do not see here on the product side that we did see when we added acid to water. When we added acid to water, we made a bunch of H pluses freely floating in that solution. When we added the HCl to our buffer, we have no free H plus formed. And basically what that means is if we don't have any free H plus formed, the concentration of H plus will stay relatively constant. And if the concentration of H plus stays relatively constant, that means our pH will not be affected either, and it will stay relatively constant as well. I say relatively constant because if you threw a pH meter into your buffer solution, you would actually see the pH go down a little bit, but it would not jump really far. So for example, if this was, say, a pH of 5, the pH of your buffer would come down maybe to like 5.9 or something like, I'm sorry, if it's 5, pH of your buffer come down like 4.9 or something like that. It won't be really, really big jump in pH. So it'll just drop a little bit. You won't see it go from, say, like a pH of 5 all the way down to like a pH of 1. So you won't have that giant jump, but you will have a little bit of a small incremental change in terms of the pH. So ultimately what's happening in this case is when we add the acid to our buffer, this H plus that comes in decides to go react with the base part of the buffer and ends up making more of the acid part of the buffer. And what that does is it leaves that concentration of H plus we started with relatively the same as to where we started with. And that's why it's able to basically resist a really big jump in pH, because pretty much all that incoming H plus gets tied up. It's no longer freely floating and won't have as dramatic of an effect on the pH as it would if that buffer part wasn't there. Question on that there. So what would happen if we did the base to the same buffer? So again, if we use the same buffer here, and again, this would be our buffer. This is our acid part of our buffer. This is the base part of our buffer. And once again, if we set up our buffer here, we would have our weak acid setting up that equilibrium in the beaker. And in this case, we're now going to add sodium hydroxide into our buffer. And that really is a source of sodium and hydroxide ions that we're going to basically add in. Now, what's going to happen in this particular case is we're going to get another reaction. It's going to be the sodium hydroxide, which is a base, is going to react with the acid part of the buffer. That's why they're called acid-base reactions, right? Not acid-acid or base-base. So If you add an acid to a buffer, it reacts with the base part of the buffer. If you add a base to the buffer, it reacts with the acid part of the buffer. So that's going to react with our acid. We're just going to get a basic acid-base reaction. So again, going to switch partners. That's going to make some water, and that will make some sodium fluoride in this case. Once again, what we made is some water, which is basically neutral. It's not going to affect the pH. We also, like we saw when we added the acid, here when we add the base, we actually make more of the base part of the buffer, which was there to begin with, so it's not going to screw up the pH. So again, it is actually what we do not see that we did see when we added it to water. When we added the sodium hydroxide to water, we produced a lot of OH minus really, really quickly, freely floating around the solution. Here, we have no free OH minus in the solution made. And that means that the concentration of OH minus stays relatively constant. And because OH minus and H plus are tied together, if the OH minus doesn't change, the H plus will stay relatively constant. And thus the pH will stay relatively constant as well. Once again, I say relatively constant because if you put a pH meter in there, you would actually see the pH go up a little bit. So if this was started at a pH of 5, you added a little bit of sodium hydroxide, maybe this one goes to 5.1 or something like that, 5.05. It will not go from 5 all the way up to like a pH of 10. It won't have this big old jump in pH because it's able to basically to resist that change. So how does that happen in this case? Well, frankly, it happens in this case when you add your OH minus from your sodium hydroxide, it actually goes and finds water. And goes and finds the H plus, and that makes our water in this case. And basically, you may be saying, but doesn't that take out the H plus in this concentration? It does. But what will happen is, like Le Chatelier's principle that we talked a little bit about, and we'll talk again, we're removing the H plus, so that's going to cause some of that HF to break apart a little bit more and regenerate some of that H plus that you're removing from the solution. And ultimately, it keeps it relatively constant. So that is essentially how a buffer works. It has to have both of those things in the solution to begin with. It has to have an acid part and a base part in the solution to begin with. And the only way to really achieve that is you have to start with a weak acid or a weak base and its conjugate partner to do that. And because it has an acid part and a base part, when you add additional acid or additional base to it, pretty much your buffer will be able to tie up any free H plus from an acid or OH minus from a base and not allow it to flow freely in the solution. So that is really how it works. It works by preventing the formation of those free ions, and that keeps the pH pretty much constant. So when you make a buffer, and like I said before, you can make a buffer at any pH you want. You actually do a calculation, which is also 1B material. You'll learn how to make a buffer at a specific pH and what you need to do that. But when you make a buffer, for example, typically speaking, you have about equal amounts of the acid part and base part. In most cases, you want somewhere near kind of equal amounts. Unlike the buffer you made in class, which was hedged one way or the other to make sure that she sat there all day and put 120 drops or 300 drops before you actually saw a change. And when you add additional acid to this buffer, it will react with the base part of the buffer, and dramatically drawn here, it will make more of the acid part. So I'll just kind of drop it like that. So you'll use the base part up a little bit, but you'll make some of the acid part of the buffer. And the same thing will happen if you add base to your buffer. It will react with the acid part of the buffer and make more of the base part of the buffer. And that is why there's something that was referred to as buffer capacity, which means that there is a limit to how good a buffer is. And when you make a buffer, you want to think about what's the concentration of like the acid or base you may be adding to it. And you want to make sure that your buffer is made up of a proper concentration to handle whatever you're adding in. Now, let's just say you were doing this and you didn't follow instructions and you just keep on adding acid to your buffer. What's going to happen as you keep adding acid to your buffer is every time you add acid, you're going to eat part of the base part of the buffer. And if you keep adding, at some point you will eat up all of the base part of the buffer. You will now not really have a buffer at that point. And if you keep adding acid at that point, now all you're doing is dropping in there a ton of H plus after you blew through your buffer. And what you would see at that point is your pH would actually change a lot and it'll have a really big jump in pH. We talked a little bit about this when we talked about titrations, as your indicator changes color really quickly as you get to the equivalence point. In a titration at the very beginning, you actually make a buffer and then you actually blow through the buffer. And that's why you see that big jump in pH. And that's why we see our indicator go from like no color to like that super pink color that we saw, because you kind of make a buffer in that titration and then you blow through it. And then it's basically, it has a really big jump in pH that occurs. Same thing would happen, for example, instead of, for example, if you we're supposed to grab like the 0.1 molar sodium hydroxide and you decide to grab like the 18 molar, it's pretty close-ish, you're just going to blow right through this acid part and it won't be able to handle it. So it's really important when you make a buffer to make sure that when you make it, the concentration of your buffer is appropriate for what you're going to be adding to it, so it's able to resist those changes. Any questions on buffers or how it works? No. All right, so that wraps up here. And again, weak acid, weak base, it prevents any accumulation of H plus or OH minus, and it's able to do that because of the weak acid and weak base component. By the way, again, you could make a buffer out of a weak base and conjugate acid. An example of that, for example, would be something like ammonia and ammonium chloride. This would be a weak base and is conjugate acid. And in this particular case, it would be the NH3 as the base part of your buffer. And here it would actually be the NH4 plus as the acid part of your buffer. Again, the difference between this guy and this guy is our Bronsted-Lowry definition of 1H plus. So the components, again, of the buffer is really only a difference of 1H plus. For example, if you made this buffer, you would start out at a pH of 9.25. It would be a basic buffer. If you made the buffer like you made the other day, the acetic acid and sodium acetate buffer, that's an acidic buffer. It would start out at a pH of like 4.74. So again, you could make a buffer at any pH you want. It'd just be able to resist changes when you add acid or base to it. Any questions on that there? All right, so equilibrium is, but you will see it really again a lot in Chem 1B. The entire class almost of Chem 1B is made up of every equilibrium you never want to know about. It's all about basically different types of equilibrium. But equilibrium in general, like we talked about last time, involves a specific type of reaction, which are these reversible reactions. And reversible reactions, again, basically means that you have an equation that is basically heading in both directions. So kind of very similar to our weak electrolytes. There again is arrows heading in both directions, which is how you know it's a reversible reaction. And it basically has, as I mentioned, a forward direction. And that forward direction is when our reactants basically go to products like normal. So the reaction is heading from reactants to products. And it also has a reverse direction. So what will happen at some point is you will start to build up enough products that the products will actually start reacting with themselves and start making more reactants and head in the opposite direction. So it's a really a sort of a two-way street. If you want to think about it that way, it's a two-way street reaction. It could go in both directions. Once again, when it reaches what is known as chemical equilibrium, it does not mean, as I might have mentioned last time when we did the experiment, it does not mean that you have equal amounts of everybody on both sides. It is actually referring to what is referred to as kinetics, which is the rate of what's going on here. And it means that the rate of the forward direction, where our reactants goes and makes products, will eventually equal the rate of the reverse direction. So basically, as quick as it would go this way, it will just turn back around and head back that way at the exact same rate. So it's going to happen basically identically heading in both directions. So what does that mean? It means that when something reaches chemical equilibrium, because as quick as it goes to the product size, it bounces back the other way. There's ultimately going to be no change in like the equilibrium concentrations of everybody. Everybody gets pretty much locked into place in terms of where they are in terms of their concentration. So again, if we started with initially like 4 molar this guy, 2 molar this guy, maybe nothing of our products in terms of molarity, and we had nothing. When this reaches equilibrium, maybe we got 2 molar this guy, 1 molar this guy, 3 molar this guy, and maybe 2 molar this guy. And what will happen is it will be able to basically just keep those concentrations. They won't continue to change because in reality they are changing, but it's just as quick as they change one way, they come back the other way. And there's like a net really of no change because the rates are equal to each other. It will be able to continue those concentrations until basically you do something to it to screw it up. And it will also fix itself if you screw it up, which is Le Chatelier's principle that we did that experiment with. But here it will continue to do so. Again, when you visually look at the beaker, it may have started maybe colorless and maybe it ended like reddish when it's all said and done. And you may look at that beaker and it may just continue to be red. And it may look to you that there's like nothing going on. It's over. The reaction is done. But there's a lot of activity of reactants going to products, products going back to reactants to keep it that red color. An example of that would be like we did the Le Chatelier's principle when I made those 5 test tubes of that like reddish solution, right? It stayed red. And that only stayed red because everybody was locked into place at equilibrium. As soon as I did something to it, like when I added some more of iron or I added some more thiocyanate, we saw the color change, right? And that's because the equilibrium was messed up. But it was able to maintain that. And again, even though when you look at it, it doesn't look like anything's happening, if you just kind of super zoomed in there, you would see reactants going to products, products going back to reactants. There's a lot of activity happening to keep something at equilibrium. So how do things react? Well, it has to do with collisions. In order for a reaction to take place, you do need some type of collision to occur. It does need to occur in the sort of correct orientation. So there's sort of, you want to think about it, active spots on these molecules, and they do have to collide in sort of the active spot of those molecules in order for a reaction to occur. They also have to hit each other with the right amount of energy. And we've talked a little bit about it when we were looking at energy. That is the activation energy. So just simply 2 guys colliding with each other may not always result in products being formed. So even though 2 reactants bang into each other, they may hit each other in the wrong spot. They may also hit each other with not the right amount of energy to actually form products. So those are 2 things that has to sort of happen for a reaction to take place. And what are ways that we could sort of ensure that reactions take place or increase the rate of a reaction? concentration is a really important thing. If we increase the concentration of something, that sort of guarantees that there's going to be a lot more collisions, and probably collisions that's going to lead to products, or vice versa, product collisions that would lead to reactants if you're going in the opposite direction. So the idea of concentration is typically if the concentration increases, the rate of the reaction will increase. And that just is because there's just a lot more guys are swimming around the solution. They don't have to travel very far to find each other to start a reaction. If you had a much lower concentration, it's going to be pretty sparse there, and it's going to take longer for everybody to find each other, to collide, and really start to react. Now, temperature also plays a really important role because, as I mentioned before, not only do you need the collision to occur, but you also need the right amount of energy. So when you raise the temperature, you're actually raising the energy. And that does a couple of things. It gives everybody in the solution a lot more energy. So they're moving around a lot faster, which means they're going to come in contact with each other a lot quicker. And they're probably going to come in contact with each other with a lot more energy than they would at, say, like room temperature, if you did it right at room temperature. And that typically would increase the rate of the reaction because of that. The opposite is true as well. If you lower the temperature, what's going to happen is everybody's going to kind of have less energy. They're going to move around less, and you're going to have less proportion of molecules that have enough energy basically to make it to the other side and of the reaction. So they're going to collide with each other, but they might not have as much energy to do so. So those are two super important things as to why a reaction will take place. And as we'll talk about, the concentration when we did Le Chatelier's principle is really what's happening, why we see those shifts occurring. That activation energy is that hill that you have to climb to get to the other side. If you remember when we talked about energy, we had two types of energy diagrams. One that looks like this, which is our reactants to our products. And this would be our activation energy. And we also had one where it looks something like this. This is our reactants, this is our products, and this would be our activation energy. This is a exothermic reaction. Exothermic because the reactants are higher in energy than the products, so the only way to get there is to release that energy, and energy is released overall. If you remember when we talked about the energy chapter, one way we represent that is with the change in enthalpy, the delta H. Delta H is negative in exothermic reactions. And that is because when you look at the difference between your reactants and your products in this case, the difference between that energy is the delta H. And one way that you calculate delta H that we talked about is to take the delta H of your products minus the delta H of your reactants. And in this case, our products are actually lower in energy. So that's going to be a lower number, and our product reactants are higher. So you're basically going to be subtracting a smaller number from a larger number. Yes, smaller is a better way of putting that. And when you subtract a smaller number from a larger number, you end up with a negative number, right? And that's why delta H is negative in this case. That is opposite than our endothermic reaction over here. Reactants are lower in energy than our products. So when we do our delta H, we will end up with a positive number because our products is a larger number minus a smaller number. And that will give us a positive number when we do products minus reactants. So that activation energy is that hill that you have to climb to get to the other side. It is also a pretty big determining factor in how fast a reaction occurs. If you have a really big activation energy, it's going to take a lot longer for everybody to get to the other side and walk up and over a hill. If you just think like you were walking a hill, you had a really giant hill, it's going to take a lot longer to get up and over to the other side. than if you had a really small hill, right? Like a speed bump in the parking lot. It's a very small hill. You get up and over the other side really quickly of that. And that's the same idea here. If that energy barrier is really large, it's going to take longer for everybody to get to their side. It also will mean that there's probably less molecules that have enough energy to actually get up and over to the other side. And if you have a smaller activation energy barrier, you will most likely see a much faster rate of reaction because there's going to be a lot more molecules that have enough energy to get up and over to the other side. So that's what's happening as we go up here. We start reacting in this reaction, and we're starting to actually break bonds as we go up the hill. But we're also starting to make bonds as well until we get to the very top. If you remember what we talked about in that chapter, that is what is referred to as the transition state. The transition state is the highest point in the reaction energy cycle. It is the peak of energy. And because it's highest in energy in chemistry, we typically do not like things to be high in energy. That is a unstable sort of situation. We definitely want things to be lower in energy. So at the transition state, this complex that's here is pretty unstable because it's pretty high in energy. And typically what will happen is it will drop down to the other side relatively quickly at that point once it gets to the top of the hill. What you have with that thing at the top is a transition state complex. It has something that has partially made bonds and also partially broken bonds. So is this really sort of transitional state complex, which is why it's called that, because you're kind of breaking those original bonds and at the same time making those new bonds. So it's really at that point where it's ready to fully break apart into sort of the new products that are going to be made on the other side of the reaction. Any questions on that there? One way that you can speed up a rate of a reaction is to add a catalyst. And a catalyst is something that, again, is not a product. It is not a reactant. And it does not get used up in the reaction. It is there simply to facilitate that reaction happening, if you want to think about it, a lot more efficient than it would if the catalyst is not there. It finds an alternative pathway for that reaction to occur. It's kind of like the big hill example, right? You go up and over the hill, like all the old cartoons. The guy finds the trap door that goes right through the middle of the hill to get to the other side. The Wile E. Coyote and the Roadrunner, right? He goes right through the middle of the hill to the other side. He's going to get there a lot quicker. And that's sort of what happens with the catalyst. It finds a more efficient way for that to occur. Catalysts are typically written on the arrow. So sometimes you may see like a metal written, which implies it's like a platinum catalyst. Sometimes you'll see H plus written, which implies the acid is the catalyst in that particular reaction. So for example, you could have a solid catalyst like a piece of metal. And what that does, for example, if you had a reaction that involved gases, is it may actually kind of attract all the gas molecules towards the piece of metal. And what that's going to do is going to bring all the molecules that need to react together kind of in the same vicinity, very close to one another. And that's going to initiate that reaction occurring a lot faster than if the catalyst wasn't there and they're just flying around. They kind of have to come find each other a lot harder because they're in all different locations flying around. But if everybody's sort of attracted to that central location of the catalyst, that's going to allow them to come together a lot more efficiently and also make the reaction occur a lot faster. Ultimately, the way a catalyst increases the rate of a reaction is it's able to actually lower the activation energy. So the result of that more efficient pathway for that reaction to take place, the activation energy hill gets a lot smaller. The result of that is there's going to be a lot more molecules that have enough energy to get to the other side, and you're going to see a lot more guys be able to actually process that smaller hill and make more products. And the result of that is your rate will definitely increase a lot faster. Any questions on rates or how to affect rates? So things like concentration could affect the rate faster or slower. Things like temperature could do the same thing, and things like catalyst are all three things that have a really big effect on the rate of the reaction. Uh,